Hello everyone, this is the video lecture for Calculus 3, section 16.7, surface integrals. I wrote up some formulas here. We got double integral of f xyz in terms of ds, so over that surface, is equal to the double integral over a region, dA, if you notice that, of fy, and then g of fy, that's a replacement for my z essentially. And then this kind of Pythagorean looking thing on the side. But if you notice, this also looks like the arc length type of formula. And so if you have f times the arc length, you get surface area, basically. This is not a surface area, it's a surface integral, but they are related in some fashion there. Another formula is just using u and v, and of course our magnitude of r sub u cross r sub v. We've seen that before as well. So the only constraint on the top one is that my g is equal to z, essentially. So g and z are the same. Okay, let's go and do some formulas. So I got 16,7,005. Well, let's do some problems. So so I got double integral over s, my surface of x plus y plus z ds is equal to something. And they say this is for a parallelogram, and they give me the equations for it. U plus v, so x is equal to u plus v, y is equal to u minus v, z is equal to 1 plus u 2u plus v, and then they want my u and v to have limits of 0 to 7, and 0 to 1. Okay, so first off, you can see that we're going to be, out of these two formulas, you probably want to use the u and v formula. And so what I'm going to do is basically just toss each of these in, and then I'm going to go ahead and find my other stuff here. So double integral of, and this is going to be a big mess, u plus v plus u minus v plus 1 plus 2u plus v, and then of course ru cross rv, and then du dv. So let's go and find out what that is. My r vector is just, of course, xyz. I mean, this is, again, old news, but my r vector is equal to xyz, which we have in terms of u and v. So I'm just basically rewriting it here. And so then I can find my derivatives, partial derivatives in terms of u and v. So I get a 1, and a 2. I'm going to cross it with, whenever I got a v, a 1, a negative 1, and a 1. So let's do that cross product. Always start with a 0. I got a negative 1k, and then I get a negative 1j, because it's a negative j component right there. 2 times a negative k would be a negative 2k, always a 0 in the middle. And 1 times 1 is a 1i. I got 2, and that's going to be a positive j component this time. I got a negative 2, 2 negatives make a positive I, and then a 0. Putting my i's together, I got a 3. My j's together got a 1. My k's together got a negative 3. So what we really need out of that is the magnitude of it. Actually, hold on. I got a 2 on my paper. Why did I have a 2 instead of a 3? Hold on. Real quick. This guy right here should be a 1, not a 2. That was a mistake. 1 times 1 is a 1. Okay. So then I got negative 1 and negative 1 makes a negative 2 right here instead. Okay. And that's why I do a little bit of math beforehand. Because you never know. Okay, so that's a 2. Well, we need to find the magnitude of this. And so then the square root, 3 squared plus 1 squared plus 2 squared. Obviously, the negatives are going to cancel anyways. We have 9 plus 1 plus 4, square root 14. And so, like way back in the day with the Jacobians, it's very similar to that. Again, it's not a Jacobian, but it's similar where we just have whatever we had and then times now square root 14. Let me go ahead and summarize all this stuff right here. We got a U, and 2 more U's to make 4 U's. So 4 U's. Oh, they kind of look the same there. My V's, these 2 V's actually cancel. I got 1 left over, so plus V, and then I think just plus 1. Times the square root of 14, du dv. You can see I put my limits in my U's and V's there. The square root of 14 can come to the front. Let's go ahead and integrate in terms of U. And so then we get 2u squared. We get a uv plus a u from 0 to 7. Obviously, the 0 is going to cancel. The 7 is going to be important to us. Oh, there's a square root of 14 right there. Sorry about that. So 7 squared is 49. Times 2 is like 98, I think. Yep, 98. I think I did things a little differently there. Okay, well, I'm just going to keep on going. So 98, and then we got a 7u, v, sorry, 7v, and then a plus a 7, dv. And that's going to be 0 to 1. Square root 14. Now let's go ahead and integrate this stuff here. I mean, I guess I could combine these guys here. Let me go ahead and do that. So 98 plus the 7 will be 105, and then plus 7v. So when I integrate now, no more integral. I got 105v plus 7 halves v squared from 0 to 1. The 0 is going to cancel. The 1 is very simple to integrate there. So 105, and then the 7 over 2. And when you put it all together, let me put all that math together. 105 plus 7 over 2, math to frac on my calculator. And any basic calculator, any scientific calculator worth its salt, I guess, is actually capable of doing the math to frac. Okay, there's your answer. Next question. 16707. So it says double integral of y ds, and that's what they want. They're giving me an r in terms of uv equal to u cosine v, u sine v, and then v. Obviously, this is x, y, and z in case anyone's wondering. They also give me limits for u and v, 0 to 6. That's a v. 0 to pi. Okay. Well, because there's so many u's and v's, you can pretty much guess that we're going to be doing our r sub u cross r sub v kind of stuff. So my derivative in terms of u would just be a cosine v, a sine v, and a 0. I'm going to cross that with r sub v. So in terms of v, I got my cosine is going to go to a negative sine, so negative u sine v. Sine goes to cosine. And then I get a 1. And so, go ahead and cross product. We always get a 0 in the beginning. Notice that we got cosine times cosine is going to be a cosine squared. So u cosine squared v k. And then I get a negative cosine v j, because that was the negative j component. Here I got, it's a negative k component, so 2 negatives are going to make a positive anyway, so u sine squared of vk, always a 0. And then I got sine, that's a positive I component, so that's easy. 0 times anything is 0. So I'm left with sine v, negative cosine v, and then my k, it's kind of weird. I got u, and then I got a cosine squared v plus a sine squared v. So you can already know that that's going to be a 1, and so that's basically 1u. Let's go ahead and start mushing all this together. Notice that my y is right here. I still got to actually plug in for y, which would be that guy. And so then I got u sine v times, and I got the magnitude of this. So let me get a little bit more room. I'm going to just say times the magnitude here, du dv. Okay, here, let's get that horizontal room that I need. So square root of the magnitude here. I've got sine squared v plus cosine squared v. And then this is just, again, 1 times u. So I'm just going to basically have a u squared du dv. Well, again, we've seen this also is going to be a 1. So u sine v square root of 1 plus u squared du dv. And again, my u was 0 to 6, and my v was 0 to pi. So we need to, of course, do like a, I would say, u substitution. We don't have u. we're already using u, so we can't do that again. So I'm going to use a double u substitution. I guess that's kind of strange, but, well, you do what you can under the circumstances. 2u du. And so you can see I'm going to divide by the 2, and it cancels with this guy, etc. So 1/2 integral 0 to pi. And when I integrate this guy, I'm going to get the 1 plus u squared to the 3/2, and I'm going to multiply it by the 2/3. Probably should have put that in the front. Still times the sine v, and I'm going from 0 to 6 dv. Well, make sure to plug in the 6 and the 0. Both are very important. The 2's are going to cancel. The 3 can come out to the front, so 1/3 now. We got 0 to pi. Plugging in the 6, I get 6 squares 36 plus 1 more is 37. So 37 to the 3/2. And then when I plug in a 0, I just get a 1 times sine v dv. This is just one big number. It can also come to the front. I don't know what that number is. And then we got 0 to pi of sine v dv. Okay, so what's my integral in terms of v? My sine will go to a negative cosine, and so, yep. Hold on, I'm working on it. 1/3. I got all this stuff here still. Okay, and then I got now a negative cosine v from 0 to pi. When I plug in a pi right there, this cosine v turns into a -1, and so I actually get 2 negatives, make a positive there. And then minus a negative will make already 2 negatives, make a positive, and this I'll get a 1. So it's kind of like, here, let me go ahead and write it out formally so you're a little bit more aware. So I have all this in the front, and essentially I got 1 plus 1, which makes 2. And so now I've got that 2/3. Instead of 1/3, I'm just going to put that in the front. 2/3, 37 to the 3/2 minus 1. And there you go. Okay, next question. 167013. I got double integral of z squared ds. And it says that S is a paraboloid. X equal to y squared plus z squared, and they're saying that x is from 0 to 4, and they want us to use, it even says use g is equal to x is equal to y squared plus z squared. At least I'm pretty sure they say that. That's what I have on my paper. If they don't say it, then I'm telling you, hey, let's use g is equal to x. It's a little different. Normally we say it's equal to z. But really, as long as you just pick one of the variables, it should be fine. So we're going to actually go back to the very first formula that we had, not the second one. So we're going to have to get my partial derivatives in terms of the other letters. So in terms of y, I get a 2y. And in terms of z, I'll get a 2z. Okay, so here we go. Let's put this all together. So double integral, z squared. Z is safe. Notice that because I'm saying my x is equal to the stuff. If I had an x in here, I'd replace it. I don't have that, so I'm just going to leave it alone. He's just z squared. And then my square root of 1 plus, and then I got my 2y all squared, my 2z all squared, dA. I mean, it's basically dy dx, I guess. Let me just clarify for you. Or dy dz or dz dy, either way. Okay, dA. Well, this is all fine and well, but I think we're going to be coming into a problem with this pretty quick. Like, if you wanted to see the picture, here's your x, and we got a paraboloid coming out here. I wonder if there's a way. See, we're looking for the area now of where that shadow would be essentially, because it's going out to 4. So that's going to cast a shadow down this way. And so if you can see, we got basically a circle. And so I want to really convert all this to polar form. Now it's going to be a little weird because it's, we're using y's and z's instead of x's and y's. But just essentially think of it kind of like an x and a y. So my r is equal to... actually, I kind of messed that one up on my paper here. My r squared is equal to that square stuff there. R squared is equal to y squared plus z squared. So I'm kind of showing you, and my r would then be going from 0 to 2. Okay, 0 to 2. And again, y 0 to 2, you can see that basically my x is going to 4. I'm saying this whole thing here is going to 4. So that's basically 2 squared. Okay. If I'm using this, then I'm also going to say, and I guess you can kind of pick, I'm going to say that my z here is equal to r sine theta. Again, I'm just picking one. I'm sure it'll work with the cosine just as well. But let's go ahead and now convert it over. This is a strange conversion to polar, but it is acceptable, and I'd say it's the best way to do it. So r sine theta, all squared, the square root of 1 plus. Notice that this will be a 4 in the front of these guys, and then that's going to be an r squared. And then I have now my requisite r, dr, d theta. So my r's are going from 0 to 2, and I'm going to full circle 0 to 2 pi. Okay. Well, if I put all my r's together, I actually get an r cubed out here. Let me show you what this will look like. So double integral sine squared theta r cubed. Now r cubed is going to be a little strange for us. We're going to work on that here in a second. Then I got my inside dr d theta. Okay. And so how we're going to work this is going to be a little strange, but just kind of, hold on with me here. I'm going to still need to do a u substitution for sure. So du is going to be equal to actually 8r dr. And so whenever I have my dr is du over 8r, now I can plug that in. You can see I'm going to divide one of them out, and I'm going to have a 1/8 come to the front. Now, back in Cal 1 and 2, I would always do these two steps. But I think I'm seeing myself in Cal 3 here through the recordings that I'm doing it less and less. It's just kind of funny to see. So this is now a u to the 1/2 du d theta. Now the problem is that I still have r's, and so I need to go and fix that somehow. If I take this here and solve for r squared, it should work. So I'm going to minus the 1 to the other side. So 4r squared is equal to u minus 1. Divide by the 4. So that's a, let's not mix it up. That's a u minus 1 and then divide by 4. So this guy here is literally plugged in right there. I don't need a square root or nothing. It's happy the way it is. Sine squared theta. My r squared is now u minus 1 all over 4. And then I got the u to the 1/2 du d theta. Whew. So, how do I now integrate this? How is this any better? Well, the thing is that you have to distribute this into both of these terms. That 4 can come out to the front as well to make a 32. And so then, we'll get to that sign here in a minute. What I have is u to the 3/2 minus u to the 1/2. Now that's acceptable. And so when I integrate these guys, no, I don't need the double integrals now. Hold on. Single integral. My sine squared will stay. And then these guys, now I have 5/2, so 2/5 u to the 5/2. And then 2/3 u to the 3/2 from, and well, I don't really know from what. I'm not using the u's here. I want to go and convert them back, of course. 0 to 2 pi sine squared. 2/5, and then I got 1 plus 4r squared to the 5/2, I believe. 2/3, 1 plus 4r squared to the 3/2. Now, from 0 to 2, d theta. Plugging into 2, even plugging into 0. I think I've been pushing it too far on the net side there. Okay, and of course my sine squared hasn't changed. So when I plug in the 2 here, 2 squared makes a 4. 4 times 4 is 16, plus 1 more is 17. And that's going to be the same over here as well. I'm sure there's a way to factor out a 3/2 power to the front. I'm not going to do that quite yet, but I got times 17 to the 5/2, and then times 17 to the 3/2. So that was that. Plugging into 0, I get a 1, and I get a 1. So it's minus the 2/5 and then plus the 2/3. Oh my. Of course, there's plenty of ways to simplify. I did it completely differently on my paper. All of this is one big number that can go to the front, and again, it's just a big old mess. And so that's okay. Notice that we'll have this right here. This integral sine squared business here. This is not too bad. There's a formula for it, but honestly, here we're on the last chapter. I just use a calculator. So this guy right here is actually super easy. He turns out to be just pi from the calculator. Okay, so that's going to make my answer a lot easier. Here we go. 1 over 32. And then I got this huge mess. You could a little bit simplify. You can pull out a 3/2 from the first two. So 2/5, and then what's left over here is a times a plain old 17. And then we got the 2/3, but only for those two. And then we still have a minus 2/5 and a plus 2/3. And then times pi, essentially now. You can clean this up a lot. My answer was pi over 16, 17 to the 3/2 times 46 over 15, and then plus 2 over 15. So there was my answer. Their answer was pi over 120, 1 plus 391 square root of 17. Their equivalent, it looks like a mess, but it'll work. So either way is fine. Okay. Next question. 167,017. So I've got double integral of x squared z. Let me write that just a tiny bit better. Z plus y squared z, and then all this ds. That's what they're wanting. And they're saying this is for a hemisphere. And they give it to me, x squared plus y squared plus z squared is equal to 9. And they're saying that as long as z is greater than or equal to 0, that's why it's the hemisphere. So just to understand, we're looking at just basically a dome going up to a radius of 3. Let's see what we can do here. So I think because I don't have a r in terms of u and v or anything like that, I'm just going to go with just that first formula like we did in the last problem. So if I can get z by itself, and here the hemisphere really helps because when you get all the stuff over to one side, it looks like this. Notice that when you square root both sides, you get positive and negative normally, but I'm going to say only positive because it's a hemisphere. This little guy here helped us out a lot in that regard. Okay. So then we're going to need our partial derivatives in terms of x and y. So, of course, the 1/2 comes to the front. Leave the inside alone. Negative 1/2 power. From the inside, you got this. The 2's are going to cancel. The negative x comes to the top. And then you got your square root in the bottom. Okay. And this is the same for zy, by the way, which we will also have to use. Okay, so we got these two. Let's go to my, back to my integral here. X squared z, y squared z. Well, the z can just come out, so I'm going to say x squared plus y squared times z. But z is this guy here, so times the square root, 9 minus x squared minus y squared. And then times the square root of 1 plus, and then these guys here, squared, essentially. Now this is just going to be one big mess. So if you don't mind, I'm going to pre-square these. The negative is going to cancel to make a positive. X squared, square root and square are going to cancel. In fact, they both have the same common denominator. So I'm just going to go ahead and do this here. Just for, like, space sake. Okay. Whew, man. So this square root, of course, extends for the whole darn thing there. We got a 1. We need to find a common denominator for that. I'm going to leave this stuff alone for a minute. I'm sure there'll be something that comes out of that. We don't need that parentheses. And I'm guessing you can also see we're going to go to polar form here in a second as well. So right here, if I put this up top, I'm going to have the 9 minus x squared minus y squared plus x squared plus y squared. And all these guys cancel now that I have a common denominator there. And what's funny is that this square root 9 on the top can come to the front as a 3. Notice that I have a square root and the square root, top and bottom. And these guys cancel. So essentially I have a plain old 3, double integral, x squared plus y squared dA. Whew, at least we got out of that. So this is much better now. I'm going to go to polar, of course, to make it a little bit better. So I'm looking for that circle on the xy plane down here. Radius of 3, you can see. So 0 to 3, 0 to 2 pi. This right here is r squared itself times r dr d theta. So that's going to be r cubed. We're going to have then r to the 4th over 4. From 0 to 3. That's a d theta. The 0 is going to cancel, but the 3 is okay. 3 to the 5th, technically. So 3 power 5 is 243 all over 4. From 0 to 2 pi of, well, 1 d theta. And so you put a 2 pi in there. The 2 is going to cancel with the 4 to make a 2 in the bottom. Only 243 over 2 pi. Okay. Wow. Next question, 167023. So I've got double integral of f vector dot ds vector equals box. It's a little different than last time, but let's just go through the process here. I got my f vector they give me is an xy, yz, xz. My s is going to be the paraboloid z equals 6 minus x squared minus y squared. And it says it's going to be above the square. So we got a paraboloid above the square, 0 to 1 and 0 to 1. I don't really, I mean, this is kind of weird looking, I'm sure, but it's a upside down paraboloid like this, but now 0 to 1 only. I don't know where this is actually going to be touching, but they want just this little square here, and so it kind of is just going down this way. There's your surface up there. There you go. And that's the shadow of it, essentially. Okay. Now that we kind of have a picture of what's going on, let's keep going. So, in order to get this thing done, I'm going to take my ds right here, and essentially ds, here's my s, kind of. My ds is going to be my derivatives of that. So like just partial derivatives and put it in a vector form. Kind of like grad. I think you can just basically say like grad z or something like that. But that's okay. Let's just go through the process. So I got xy, yz, then xz, and then notice that my formula essentially is going to be a positive gx, a positive gy, and then a 1 dA. So I'm converting this over to this. Again, I'm just essentially taking my derivatives there. Notice I got positives and stuff. I can't remember if somehow I maybe did it wrong earlier and like switched my signs, but obviously we're in positive land here. I don't see any reason why not to have that. It's an orientation, I guess, issue. Y, Z, X, Z, dot. Okay, what's my derivative in terms of the X? It's going to be a negative 2X. My derivative in terms of the Y is a negative 2Y. And then 1. Now this is interesting here because I went and did this right here as it was, and I was getting it wrong. What you actually need to do is keep these positive right there. Okay? These are strange. These are strange. It's weird to have the positives there because we already said, oh, do the partial derivative. I'm trying to focus on the fact that they're positive. Why exactly? Again, if you would have to go back to the formulas. I don't think I wrote this one down perfectly from the beginning, but that's okay. I'm just saying it's an orientation issue. And I thought that we have seen this before, and you would see like a little negative 1 at the end, especially for your tangent planes. That's the other place I've seen it. I'm going to move on, though. Keep it positive. So whenever I do my dot product, I get xy times this, so I get 2x squared y plus. Here I'm going to get the 2y squared z plus. And then I have here, we'll just times 1, so xz. So obviously we need a dA, and we got 3 variables. We need to replace our z's. And of course you know what my z is equal to. So we're going to have one really big mess here in a second. 2x squared y plus 2y squared, 6 minus x squared minus y squared. And then we got an x, and then 6 minus x squared minus y squared dA. Which again, might go to polar in a minute, maybe not. So in order to keep going, I'd have to distribute this one here as well. Again, this is just one really large mess. 12y squared minus 2x squared y squared minus 2y to the 4 plus 6x minus x cubed minus xy squared dA. Okay. So now I'm going to integrate. Let's not do dA. Let's do dy dx. That'll probably be better. And so, and dy dx is easy because it's just 0 to 1, 0 to 1. They already told us that. So let me go ahead and actually do my first integral. Sorry, I didn't want to erase it. So in terms of y, this is staying 0 to 1. In terms of y squared over 2 to 2's cancel, so x squared y squared. Here we got cubed over 3. The 3 cancels with that to make a 4, y cubed. Here I got the divide by 3, so 2/3, x squared y cubed. Here again I got the 5th, divide by 5, so 2/5, y to the 5th. There's no y's there, so 6xy. No y's there, so x cubed y. And then again, divide by the 3/1/3 xy cubed. Go and fix that cubed. From 0 to 1, dx. Now, the 0 cancels everything, obviously, but the 1 is important because you want to retain your variables. So this is just a 4 now. 2/3. Oh, that's going to be a minus. Sorry. See how I changed the sign there? 2/3 x squared. 2/5 by itself, 6x minus x cubed minus 1/3 x dx. I don't want to like waste your time here, but essentially at some point you got to use a calculator to make it a little easier. But I mean, it's just polynomials at this point. I just wanted to do it really quick. So 1133 divided by 180. I believe that I had a couple issues trying to figure out where my all my variables went on this one. So just watch out. Like you got a cube here, and then you got these two squares there. You know, you got a regular x's here and there. You know, you got some numbers. So just watch every term. I think I mixed up and messed up one term, like I just forgot about it. And you could easily do that and mess the whole problem up. So watch out for that. Okay, last question, 167027. So I've got double integral of f vector dot ds, just like last time, equals something. My f vector is equal to 0, y, negative z. And they say that my s is equal to y equals x squared plus z squared. And they say y is equal to y is from 0 to 1. That's a paraboloid. And then they also say something about a disk, x squared plus z squared less than or equal to 1 as long as y equals 1. I believe that they're trying to enclose this. So what's going on is that we have this paraboloid here along the y's, and then see my disk here, my disk. And so I'm pretty sure it's like enclosing itself off. And so let's go and do this formula here. I need my ds to be converted. So first off, 0, y, negative z, and then I needed to go dot. And so just like the last time, I'm going to take my partial derivatives of my y right there, and I'm going to keep them positive here. Everything's positive. Just keep it positive. It's easy enough. So 2x, 1, and then 2z. Again, why did I get a 1 right there? It's just because it was, just like in the last one, my z had a 1 right there. It's the same thing. I just have a 1 sitting right there. It's kind of like the tangent plane stuff again, where you have your partial derivatives, and the last one's just going to be a 1. It's just part of a formula and an orientation. And so let me go ahead and dot product this here. Anything times 0 is 0. Y, and then I got negative 2z squared dA. So notice that I have a y in there. I need to not have that y, and they told me what y was equal to. So let me just replace it. X squared plus z squared minus 2z squared dA. These guys combine to make x squared minus z squared dA. So that's not too bad. I'm going to go ahead and convert everything to polar mode. So x is going to be equal to r cosine theta. My z is equal to r sine theta. I'm just reminding you this stuff, okay? I think that's actually all we need in this particular case. So if that's the case, if I'm going to polar, notice that I'm going from my y equals 1. If I put it in there, what's my radius? It's going to be a 1, so 0 to 1 for my radius, 0 to 2 pi for a full circle of, and then I've got now r cosine theta all squared minus r sine theta all squared, and all this times r dr d theta. So I have a r squared and r squared. I can pull it out, and then I still then have another r to make an r cubed. Just go ahead and write it for you. And then I got cosine squared minus sine squared d theta. Oh, dr d theta. Do you see something kind of interesting? Look at this guy right here. That's actually going to end up being cosine of 2 theta. I'll do that here in the next step. But yeah, all this here is cosine of 2 theta. That's one of those trig identities. It'll just make it easier to integrate later. So in terms of r, I get r to the 4th over 4. So I got a 1/4 in the front, 0 to 2 pi. Notice I'm going to plug in the 1. So essentially I just get a 1 to the 4th, whatever. Cosine 2 theta d theta. And at this point, it's much easier to integrate this guy. So my cosine, when I integrate, is going to go to a sine. But again, because of the inside and doing like a u substitution, don't know why I did a 2 there, you're going to have a 1/2 now sine of the 2 theta from 0 to 2 pi. And when you plug in the 2 pi, you're actually going to get a 0. And when you plug in the 0 into this thing, you're going to still get a 0. And so the whole thing went to a 0. Wow. Well, we're done. Thank you very much. Have a great day.